We'll start our discussion on phases here, starting with the gas phase. Starting with the basics. Gas is noted as the least dense phase of matter, and it conforms to the shape of its container and is compressible. There are some pressure equivalencies that you do have to take note of, and those are listed below. You will often not see kilopascals, but just make sure you're aware of it. A mercury barometer is quite simply a barometer or some sort of column filled with mercury. An increase in pressure will increase the height of mercury. Now, how is this done? This is done because of the atmospheric pressure on the outside. The atmospheric pressure creates a downward force on the pool of mercury at the base of the barometer, while the mercury in the column exerts an opposing force, which is its weight, based on its density. The weight of the mercury creates a vacuum at the top of the tube, and when the external air exerts a higher force than the weight of the mercury in the column rises. When the external air exerts a lower force than the weight of the mercury, then the column falls. This is how a reading can be made, by obtaining the measure of height of mercury in millimeters, which is directly proportional to the atmospheric pressure being applied, which is why millimeters of mercury, mmHg, is often a common measure of pressure. In general on the MCAT though, you're going to see atmospheres. We can't talk about the gas phase without talking about the ideal gas law and what it entails. An ideal gas assumes negligible mass and volume and is noted at STP, conditions of which are listed below. Because of this, 1 mole of gas is always going to be noted as 22.4 liters at standard temperature and pressure. The ideal gas law is listed below as PV equals nRT, or as I like to remember it, PivNert. Pressure times volume equals number of moles times the gas constant times temperature. What you're going to notice though is that the ideal gas law was derived later on, and there were other principles that came before it, which is how the ideal gas law came into fruition. These are noted below. What you will notice is that all these, the Avogadro's principle, Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law can all be derived from the ideal gas law. So let's do a few examples. For this situation, now I'm going to write the ideal gas law up here so we can have it for reference. PV equals nRT. For this situation, pressure and temperature are all going to be the same. Now, if we were to look at number of moles, we could run this derivation like so. So R is a constant, and P is constant as well. So we would ignore these. So if we had V1 equals N1 to some sort of constant, let's use constant T, and we had another situation like so. I could solve and set this equal to T. So if I were to run that accordingly, divide N1, that's V1 over N1 equals V2 over N2. And this is possible because we set it equal to T. Obviously, you can do this with pressure as well. If we were to invert this, then we would get Avogadro's principle. Boyle's law is done in much the same way. So if I were to do Boyle's law, P1V1 equals N1 R T1. And if I were to have P2V2 equals N2 R T2. If I were to say that N and T were the same, then I could set these two expressions equal to each other and just exclude the middleman, therefore getting Boyle's law. The same can be done for Charles' law, Gay-Lussac's law, and combined gas law, but I won't bore you any further with that. Just remember that if you know the ideal gas law, you can use that to calculate and derive the other laws. The MCAT's generally not going to ask you the exact name for these laws, so I would just place your bets and hinge on knowing the ideal gas law. If you know the ideal gas law, you can derive these other relations as well. Dalton's law of partial pressure is listed below. It simply states that pressures are additive, meaning that the portion of a compound that constitutes the entire pressure is going to be indicative by a percentage. And the partial pressure is noted as the moles times the pressure total. So it's the mole fraction times the pressure total. Henry's law is a little bit more complicated, and it's not often seen mathematically on the MCAT. However, you will see it spoken of conceptually. It simply states that the amount of gas dissolved in solution is directly proportional to the partial pressure of the gas at the surface of the solution. So if I know the partial pressure of the gas at the surface, then that has to be proportional to the amount of gas dissolved, and the equations for which are listed below. A is the concentration of A in solution, Kh is the Henry's constant, which will be provided to you, and Pa is the partial pressure of A. Note that the value of Henry's constant depends on the identity of the gas, which is why it will be provided to you. Note as systems change over time, they're set equal to that constant. Therefore, you can get the equation A1 over P1 equals A2 over P2. It simply states that there has to be a proportional change. We're going to go into the kinetic molecular theory, which is basically relying on assumptions about gas particles. They state that gas particles have negligible volume, don't have any intermolecular attractions, and they undergo random collisions with each other and their container. It also states that those collisions are elastic and the average kinetic energy is proportional to the temperature. Note that these are massive assumptions made, which is why the ideal gas law works. Also note that as these conditions are increasingly not met, you're going to see increasingly more deviations from ideal behavior. Kinetic energy, if you remember from our physics module, is listed as 1/2 mv squared, or in the case of kinetic molecular theory, 3/2 k sub b, or the constant, times T. Kb, if you remember, is the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules over Kelvin. This is a bridge between the macroscopic and the microscopic behaviors of gas. Take note that if you have to use the Boltzmann constant, it's going to be provided for you. We'll briefly touch on root mean square, but it's not really commonly seen. So the equations are listed below, and it's simply stated as the average speed of a gas. And if you remember this, great. If you don't, it's not too big of a deal. What you do need to have a good understanding of is Graham's law, which simply states that gases with lower molar mass diffuse or effuse faster than gases with higher molar mass at the same temperature. This rate is given below by this expression. A good way to think of this is if you were to take people and have them run around a room. If you were to take a bunch of 8-year-olds full of energy and sugar, these are smaller than a morbidly obese group of individuals. So if I were to let them loose, these 8-year-olds would run around the room and bounce around faster than would these overweight individuals. So it's a good way to think about it. Just picture a more realistic situation. Diffusion is noted as the spreading out of particles from high to low concentration, whereas effusion is the movement of gas from one compartment to another through an opening. Obviously, effusion is going to occur until a state of equilibrium is reached. That is, that there is an equivalent amount of gas in both containers. Diffusion is also going to obey equilibrium. Particles are going to spread out until the concentration is equal across the entire area. Finally, we're going to talk about real gases. These are deviations from ideal behavior. So if you remember our assumptions made by the kinetic molecular theory, these are situations in which those assumptions are not going to hold true and our values are going to be not ideal. This will occur at high pressures or low temperatures. And why would that be? Well, at high pressures, gases are less free to move around. Therefore, they're not going to have as much room to go about, which is obviously going to deviate from the assumptions and therefore deviate from ideal behavior. At low temperatures, there's going to be less energy in the system, meaning they're not going to be moving as much, fewer collisions, which would also decrease ideal behavior. The van der Waals equations of states is a correction of the ideal gas law. However, you often will not see this on the test, and if you do, it's going to be provided for you. Quite simply, it takes into account deviations from ideal by incorporating A and B, which are physical constants that are experimentally determined for each gas. The A term corrects for the attractive forces between molecules, and it's obviously going to be smaller for gases that are small and less polarizable, and larger for gases that are larger and more polarizable. The B term corrects for the volume of the molecules themselves. Take note that if you have to use this equation, it will be given to you, and these constants will be provided. The main takeaway from our discussion of real gases is to take note of what conditions are going to cause deviations from ideal behavior. We'll finish up our discussion of the gas phase right then and there. In the next lecture, we're going to go into the liquid phase, or solutions.